So I'm here to talk to you about what are some first steps you can do if you are a programmer who suddenly needs to learn machine learning. Maybe it's for a personal project you're interested in trying, or maybe as part of your job, your company's like, hey, let's try this new machine learning thing, and your team's going to figure it out. So the good news is while machine learning is based on a lot of math, you don't have to start by digging out your old math textbooks. You can actually start by doing a little bit of it, implementing something, learning a little bit more. And so, yeah, essentially, to get started, you need a basic idea of how it solves a problem, what problems it's good at solving, and you need enough data to train it. And so I'm going to talk to you a little bit about some of those first steps. So probably the most important thing is what is the difference between machine learning and your traditional programming. So in your programming, you're telling a computer what to do line by line, step by step. Everything's very explicit and spelled out. In machine learning, you're teaching the computer to make decisions without programming them. You're trying to do this by showing it a lot of examples and having it learn from those examples. So we're trying to sort of replicate how humans learn. Like, no one programmed you as a child to learn to tie your shoes. Someone showed you how to do it, you tried it and you failed, and they showed you what you did wrong and you tried again. And so we're trying to do that same basic thing with computers. So a little more into this, maybe you've heard the exercise or metaphor sometimes used for new programmers. How would you teach a computer to make a sandwich? So the basic idea is that computers do exactly what they're told, but nothing more than what you told them. So the students give instructions, and the teacher acts it out to comic results. So if they forget to say to take the peanut butter and the jelly out of the jars, you've got jars of peanut butter and jelly between two loaves of bread. Or if so you take the knife and get the peanut butter out of the jar, but don't tell you to open the lid, maybe you start stabbing the peanut butter. And so this is a, entertaining exercise for new programmers. This is also kind of where machine learning comes in, because this doesn't have to be just a metaphor anymore. People are actually programming robots to do things like make sandwiches. There's definitely a pancake flipping robot. I've seen videos. And so at the end of this exercise, you haven't actually programmed a computer to make a sandwich, because there's still more steps. There's how do you pick up a knife? How do you know that's a knife? What do you do if the next time you go to pick it up, it's rotated slightly from the way you were taught in the first place? And so that's where the teaching by example of machine learning comes in, that you don't want to or can't program all of those steps and account for all of those edge cases. So something to think about if you are tasked with a machine learning problem is my problem actually a good fit for machine learning? You can't just throw it at everything and have it solve all your problems. I would like it to, maybe someday, not today. So some cases where machine learning could be a really good idea and help you out a lot, if you have a lot of data or examples. So if you're trying to teach it by showing it examples, you want a lot of examples of here's a scenario, here's what you do in this situation. If there's too many edge cases or it's too complicated to explain with a set of rules or by a math problem, also good for machine learning. And you have to have informative data to teach the computer. So it's not just enough to have a lot of examples. Your examples have to be... Oh, I didn't realize my fonts got messed up. Sorry, when I switched computers. Hopefully it's kind of legible. Anyway, your data has to have useful information. You can't just do a web scrape and give it the internet and say, learn from this. It has to be relevant information to what you want it to do. And so kind of the opposite of that, so you wouldn't want to use machine learning if you don't have a lot of data to show the computer, or if you can already solve the problem with some math or some series of if statements, or if you have data that doesn't really convey what you want the computer to do. So something it's really good at are things like, is this a cat or a dog? Humans are really good at this. You look at a picture, that's a cat or that's a dog. It's really easy and really quick. But how would you describe how you know that something's a dog? Is it the ear shape? It's got floppy ears, but some dogs have pointy ears, and so do cats. Is it the nose length? If you could program a computer to calculate the length of an animal's nose from a picture, maybe dogs have longer noses until you start getting into pictures of bulldogs, and then, that's all out the window. But machine learning is really good at this, even though you can't explain exactly what makes this a dog. Some bad examples are, I mentioned if something is a math problem, complicated or not, computers are already really good at math. Don't waste your effort trying to find a machine learning problem to do this. Just use the existing tools. So a common oversimplified guideline is if a human can assign something a label or a value in less than a second, it's probably a good candidate for machine learning, something that's instinctive and hard to describe. So now that we know a little bit about what machine learning is and does, but what does it actually look like when you go to program it? So I managed to do an overly simple example in about 5 lines of code. I want to hope they're still legible. So probably the most important part is you need to import things from the scikit-learn library. It's amazing, and it takes care of all of the complicated math and just puts everything into a really nice package for you. So you use scikit-learn, and you create your machine learning model, this ML model variable. And so there's a lot of different algorithms available. This particular example is called SVM, or Support Vector Machine. And so all these different models, what they are and what they do, are often covered in machine learning talks. So I'm actually not going to go into much about that today because there's a lot of information available. You also have to get your data. So you would usually import it from a large CSV, not just hard-coded into your code. But here, I'm just showing that you have examples. So I have 5 pairs of numbers, and then you also need labels. So does this pair of numbers belong to group 0 or group 1? And so data is most of what I'm going to talk about today. But the last step in actually making your model is you have to train it. So pretty much everything in scikit-learn is going to have a fit method. So it's model.fit, give it your examples, give it your labels, voila, you have a machine learning algorithm. And so this last part is probably what's talked about the most. How does it work? What is it doing? There's a lot of information on how this kind of stuff works. So if you actually want to use your model, it's 2 more lines of code. You have to get some more examples, 2 more pairs of numbers. And then this model also is going to have a predict function. You give it model.predict, give it your new data, and it guesses at what group, 0 or 1, those 2 numbers should be in. So now you have a machine learning model in 7 lines. But what is it doing? So I mentioned I wanted to talk about the data portion. And that's lovely. But the point is, your data is more important than your algorithms. So there was a survey a couple years ago, 200 data scientists, and they found out that like 50 to 80% of their time is just cleaning up their data. It's not playing with fancy algorithms. It's gathering data, cleaning it, making sure it's ready. They also generally said it was their least favorite part of the job. So people being people, they're not going to do something they dislike for that much of their time unless they really, really have to do it. And they do it because your data determines the accuracy of your model. If you train it on garbage information that's not true or is otherwise corrupted, it's going to learn garbage from that data. Or even just, maybe it's not garbage, but there's a simple mistake. Or finding accidental patterns. There was one group that really wanted to tell the difference between a husky and a wolf. They're very similar looking. It can be hard to do. And so they train this classifier, and the results are great. It's really good at telling, this is a wolf, this is a husky. Until they looked into how it was working, and it was not telling the difference between a husky and a wolf, it could tell whether or not there was snow in the picture. Because almost all the pictures of wolves, there was snow in the background. This isn't what they wanted it to do, but until they took a closer look at their data, they didn't realize they'd taught it something unintentional. So the last thing your data does is it's going to determine the type of machine learning algorithm you're going to use. So in this example, we have different categories. So you could cat or dog, group 1 or group 2. That's going to have a different type of model than if you want to predict a value like, what does something cost? What's the price of this thing? So it's very important in also choosing what type of machine learning you're going to do. So taking another look at our oversimplified data. So I mentioned we have 5 examples. The 3 have the first number is larger, so it's 309342, and those all have a corresponding label of 0. The last two, the second number is larger. We have 23 and 89. But there are a lot of problems with this little fake data set. There's way too few examples. You're usually going to want at least 50, and if you have a bunch of different categories to put your data in, very possibly you'll need more than that. There are also some missing cases. We haven't told it anything about what to do if the numbers are equal. What is it supposed to do then? What group does that go in? Is there a different group? How does it handle that situation? And your goal's kind of unclear too. So sort of like with the Husky problem. So you could interpret it as whenever the second number is larger than the first, you put that in group 1. But what if it's not about that? What if it's that the numbers are consecutive? What if 8-9 belongs in group 1 and 8-10 goes back to group 0? Or what if they're just off by 1? So 2-3 and 3-2 belong in the same group. We haven't given it enough information to learn what we really want it to do. The other issue with our data is we don't have any way to evaluate our model. We just have this one group of data, we train on it, but how do we tell how well it's doing? So what you need to do is you need to actually have 2 sets of data, one that you train on with that fit method, and another one that you use to test and see how well its predictions match up to what the labels should have been. If you don't do that, and you try and test on the data you trained on, it's a lot like if your teacher, your professor, had ever given you a practice exam and then gave you the exact same exam the next day. Like, you could just memorize the answers in the order, and you haven't actually learned anything useful. Okay. So those are just some beginning steps for machine learning, and I just wanted to put all of the steps kind of together. So if you find yourself like, hey, I need to or want to learn machine learning right now, some things to consider are, is my problem even a good fit for machine learning? And if it is, can I get enough high-quality data to teach it anything useful? And don't forget to clean your data. And there's a lot of information on cleaning data, but it's essentially making sure all of your labels are correct, there's nothing missing, and everything's good to go. Then you want to choose your algorithm based on your data, and start simple. Start with something that's easy to implement and works very quickly, and see how that works. And if it works well, maybe try something similar. If it's not working, try something a little different. Maybe that'll work better. And just try it out and play with it, and learn as you go. Try out an algorithm, learn a little bit about how it works. And so this is only 15 minutes, but I put together some resources, and I tried to focus on ones that are either more practical based or for beginners trying to get into the field. I really enjoy the podcast Practical AI. It's a podcast, so you can't get too technical, and then they'll usually have a corresponding page where there's links to all the things they talked about if you really want to learn more about the technical details. Scikit-learn is the package where you import everything from, and they have great documentation available. If you're really into neural networks, the big buzzword, there's an online website, Neural Networks and Deep Learning, that's very kind of hands-on based that I enjoyed. Pythonprogramming.net is a website that's some good information. And I thought this was a really interesting Coursera course. It's called Structuring Machine Learning, and it's all about you have a machine learning project and how do you approach it. So it's not so much on the algorithms and how they work, it's on how you solve a problem and what do you do if it's not working the way you want it to. And that's something that's not covered quite as much in a lot of these tutorials, so I thought that one was particularly interesting. So that is what I have. I'm happy to answer any questions in my last minute or later tonight.
Yeah, so you get 1 more minute for questions. Also, I forgot to mention, if you've got questions, feel free to go to slido.com and put in that tag, and the questions will pop up on the screen, and the presenter can speak to them. So if anybody has questions, yeah.
So scikit-learn's a great tool for supervised and unsupervised learning. If I'm trying to build a controller, sort of like what Android does, like I want to solve an MDP or a partially observable Markov decision process, do you have a library or a resource you recommend for solving that kind of problem in the machine learning space?
I don't, unfortunately. I've actually never worked with that, but it sounds really cool, and I hope you find one, or maybe someone else knows one.
Anybody else got questions for Alyssa?
Do you know what classes might be useful at an undergraduate level, whether it's math or programming for machine learning?
I would say if there is a machine learning course with a good professor, I would definitely take it. Because there's something about hands-on and actually learning the machine learning. I think being a good developer has been really helpful, at least when I left academia and went into industry. Being able to build a system that supports this algorithm is just as important, if not more, than having an algorithm that works. The math is somewhat important, but like I said, you can kind of learn just what you need to get something going. But yeah, machine learning courses, if you can do it, and definitely like programming and building things, yeah.
I got one question from Slido, and I think that'll be the wrapping it up.
Do I have any advice for mitigating missing data?
Go find it.
That is the ideal option. It also kind of depends on what kind of data you have. So if it's like an Excel array or a CSV file, you can sometimes guess at what the data should be. So you can do like an average of what that data usually is and everywhere else. I think there are a few algorithms that let you just have empty data, but there's not many. It also gets interesting if you have like time series data. Maybe it's missing because your sensor's saturated at a certain time. I always had to wind up just deleting that whole section if it's saturated. Like I couldn't find a good way of getting that back.
All right. Well, one quick question. Hold on. Let's put it on the recording. Okay.
So one of the things that I've found helpful with mitigating missing data is using distribution plots to find out where the distribution of the missing data is, as well as box plots, because they give you averages, they give you quartile ranges, they give you your outliers and things of that nature. So that's very helpful as well.